So filtration, an average of 21% of the blood pumped by the heart each minute flows through the kidneys. Of the total volume of blood plasma that flows through the glomerular capillaries, about 19 passes through the filtration membrane into the Bowman capsule to become filtrate. In all the nephrons of both kidneys, about 180 liters of filtrate are produced each day, but only about 1% or less of the filtrate becomes urine because most of the filtrate is reabsorbed. Filtration is a non-specific process whereby materials are separated based on size or charge. A simple example of size filtration is demonstrated by a drip coffee maker. In this case, the driving force of filtration is gravity. The kidneys also use size filtration to remove substances from the blood by filtering it. But in this case, the driving force of this filtration is blood pressure. The filtration membrane allows some substances, but not others, to pass from the blood into the Bowman capsule. Water and small solids readily pass through the opening of the filtration membrane, but blood cells and most proteins which are too large do not enter the Bowman capsule. One example of a small blood protein that can enter the filtrate in very small amount is albumin. Consequently, the filtrate contains more cells and little proteins. The formation of filtrate depends on a pressure gradient called the filtration pressure, which forces fluid from the glomerular capillary across the filtration membrane into the Bowman capsule. The filtration pressure results from forces that move fluid out of the glomerular capillary into the Bowman capsule minus the forces that move fluid out of the Bowman capsule into the glomerular capillary. The glomerular capillary pressure is the blood pressure in the glomerular capillary. It's the major force causing fluid to move from the glomerular capillary across the filtration membrane into the Bowman capsule. There are two major forces opposing the movement of fluid into the lumen of the Bowman capsule: capsular pressure and colloid osmotic pressure. The capsular pressure is caused by the pressure of filtrate already inside the Bowman capsule, and the colloid osmotic pressure is within the glomerular capillary. Because most plasma proteins do not pass through the filtration membrane, they produce an osmotic pressure that favors fluid movement into the glomerular capillary from the Bowman capsule. Therefore, the filtration pressure is calculated as follows: glomerular capillary pressure, capsular pressure, colloid osmotic pressure, filtration pressure. The filtration pressure forces fluid from the glomerulus into the Bowman capsule because the glomerular capillary pressure is greater than both the capillary and the colloid osmotic pressure. Under most conditions, the filtration pressure remains within a narrow range of values. However, when the filtration pressure increases, both the filtrate volume and the urine volume increase. And when the filtration pressure decreases, both the filtrate volume and the urine volume decrease. The filtration pressure is influenced by the blood pressure in the glomerular capillaries, the blood protein concentration, and the pressure in the Bowman capsule. The blood pressure is normally higher in the glomerular capillaries than it's in most capillaries. The filtration pressure increases if the blood pressure in the glomerular capillaries increases further. The filtration pressure decreases if the blood pressure in the glomerular capillaries decreases. The filtration pressure is also influenced by the concentration of proteins in the blood. An increase in blood protein concentration encourages the movement of water by osmosis back into the glomerular capillaries and therefore reduces the overall filtration pressure. On the other hand, a decrease in blood protein concentration inhibits the movement of water by osmosis back into the glomerular capillaries, which increases the overall filtration pressure. Regulation of filtration. The blood pressure within the glomerular capillaries is fairly constant because the afferent and efferent arterioles either dilate or constrict to regulate the blood pressure. There, even though the systemic blood pressure may fluctuate substantially. Also, the concentration of blood proteins and the pressure inside the Bowman capsule are fairly constant. As a consequence, the filtration pressure and the rate of filtrate formation are maintained within a narrow range of values most of the time. Tubular reabsorption. As the filtrate flows from the Bowman capsule through the proximal convoluted tubule, loop of Henle, distal convoluted tubule, and collecting duct, many of the solids in the filtrate are reabsorbed. About 99% of the original filtrate volume is reabsorbed and enters the peritubular capillaries. The reabsorbed filtrate flows through the renal veins to enter the general circulation. Only 1% of the original filtrate volume becomes urine. Because excess ions and metabolic waste products are not readily reabsorbed, the small volume of urine produced contains a high concentration of ions and metabolic waste products. The proximal convoluted tubule is the primary site for the reabsorption of solids and water. The cuboidal cells of the proximal convoluted tubule have numerous microvilli and mitochondria, and they are well adapted to transport molecules and ions across the nephron wall by active transport and cold transport. Substances transported from the proximal convoluted tubule include proteins, amino acids, glucose and fructose molecules, as well as sodium, potassium, calcium, etc. The proximal convoluted tubule is permeable to water. As solid molecules are transported out of the proximal convoluted tubule into the intestinal fluid, water moves by osmosis in the same direction. The solids and water then enter the pretubular capillaries. Consequently, 65% of the filtrate volume is reabsorbed from the proximal convoluted tubule. This descending limb of the loop of Henle further concentrates the filtrate. The renal medulla contains very concentrated interstitial fluid that has large amounts of sodium and chloride and urea as well. The wall of the thin segment of the descending limb is permeable to water and moderately permeable to solids. As the filtrate passes through the descending limb of the loop of Henle into the medulla of the kidney, water moves out of the nephron by osmosis, and some solids move into the nephron by diffusion. By the time the filtrate has passed through the descending limb, another 15% of filtrate volume has been reabsorbed, and the filtrate is as concentrated as the interstitial fluid of the medulla. The reabsorbed water and solid enter the vasa recta. The ascending limb of the loop of Henle dilutes the filtrate by removing solids. The thin segment of the ascending limb is not permeable to water, but it's permeable to solids. Consequently, solids diffuse out of the nephron. The cuboidal epithelial cells of the thick segment of the ascending limb actively transport sodium out of the nephron, and potassium and chloride are co-transported with sodium. The thick segment of the ascending limb is not permeable to water. As a result, sodium, potassium, and chloride, but little water, are removed from the filtrate. Because of the efficient removal of these solids, the highly concentrated filtrate that enters the ascending limb of the loop of Henle is converted to a dilute solution by the time it reaches the distal convoluted tubule. As the filtrate enters the distal convoluted tubule, it's more dilute than the interstitial fluid of the renal cortex. Also, because of the volume of filtrate reabsorbed in the proximal convoluted tubule and the descending lip of the loop of Henle, only about 20% of the original filtrate volume remains. The solids transported from the ascending limb of the loop of Henle enter the interstitial fluid of the medulla and help keep the concentration of solids in the medulla high. Excess solids enter the vasa recta. The cuboidal cells of the distal convoluted tubule and collecting duct remove water and additional solids. Sodium and chloride are reabsorbed. Sodium ions are actively transported and chloride ions are co-transported. Also, 19% of the original filtrate volume is reabsorbed by osmosis, leaving about 1% of the original filtrate as urine. The reabsorbed water and solids from the distal convoluted tubule enter the peritubular capillaries and the vasa recta from the collecting ducts. The reabsorption of water and solids from the distal convoluted tubule and collecting duct is controlled by hormones which have a great influence on urine concentration and volume. In summary, most of the usable solids that pass through the filtration membrane into the Bowman capsule are reabsorbed in the proximal convoluted tubule. Filtrate volume is reduced by 65% in the proximal convoluted tubule and by 15% in the descending limb of the loop of Henle. In the ascending limb of the loop of Henle, sodium, potassium, and chlorides, but little water are removed from the filtrate. Consequently, the filtrate becomes dilute. In the distal convoluted tubule and the collecting duct, additional sodium and chlorides are removed. Water moves out by osmosis, and the filtrate volume is reduced by another 19%, leaving 1% of the original filtrate volume as urine. Tubular secretion. Some substances, including byproducts of metabolism that become toxic in high concentrations, and drugs or other molecules not normally produced by the body, are secreted into the nephron from the peritubular capillaries. And with tubular reabsorption, tubular secretion can be either active or passive. For example, ammonia diffuses into the lumen of the nephron, whereas hydrogen, potassium, creatinine, histamine, and penicillin are actively transported into the nephron. Hydrogen ions are actively transported into the proximal convoluted tubule. The epithelial cells actively transport large quantities of hydrogen across the nephron wall into the filtrate. The secretion of hydrogen plays an important role in regulating the body fluid pH. In the proximal convoluted tubule, potassium is reabsorbed. However, in the distal convoluted tubule and collecting duct, potassium is secreted, resulting in a net loss of potassium in the urine. Alright guys, subscribe to my channel, put your comments on the comment section, give me a likes, bye bye, see you.